last problem on the sheet. Well, actually, there are two of them. And that last, the hardest of all of them. Yep, we saved the best for last. Now, before we dive into that, we need to learn a little bit about what's called specific heat capacity. Abbreviated CP in this equation. Need to know it. Specific heat capacity. Not Pacific heat capacity. Talking about specific. Okay, not talking about oceans here. Okay, focus, people, focus. Now, specific heat capacity, you know something about it. You do. You do. You know that if you were to take a aluminum ladle, like an aluminum spoon, and stick it in a roaring fire and hold on to it tight. See how that turns out for you. How long can you hold on to it? Not very long. How do I know? Did that, Boy Scouts. Yeah, I've done it. Trust me. You can't hold on to it very long. Why? Because metal heats up very quickly. Very quickly. It doesn't take much heat to heat up metal. We know that. You do. You know that. Metal gets hot very fast. It also cools down very fast too, which is good. So if you got like aluminum foil wrapped around something in the oven, you take that something out and let it sit for a minute. You touch the aluminum foil, like, you got nothing aluminum foil. You got nothing. You're not hot at all. Not like me. Hot, hot, hot. I'm Brad Pitt hot. Sorry, I'm going off on a tangent. I'm just getting tired here. Okay, Firestone. I'm definitely Firestone. Not Michelin. Tired. Get it? It's funny. Tired. Okay, keep going. Now, we also know that water takes a long time to heat up. I know what you're saying. No, it doesn't. I want to make my ramen noodles, and I only have to water for 5 minutes, and it's boiling. Yeah, 5 minutes. That's a long time for something to get warm. Water takes a long time. Trust me. If you don't believe me, try something else. Try alcohol. Take rubbing alcohol, put it in a pan on the stove, turn it on, and see how long it takes to boil. No, actually, don't do that because bad things will happen to you, and I'll get blamed. No, don't do that. Okay, just trust me. Water takes a long time. So there are different values for specific heats. Aluminum, that's pretty high. That is 900 joules per kilogram. That's actually pretty high for a metal. For a metal, that's pretty high. You get things like copper, 385. Okay, lead. Lead is down around 160, I believe. You don't need to know these. You can always just look them up. You don't need to know. And there's zinc and iron. They're around the 400s or something like that. But water, H2O, is 4,190 joules per kilogram. Look at how much higher water is than all these other things. Why? Because it takes a lot of energy to heat water up. We know that's true because we think about it. Water is used in the cooling system of an automobile. You use it in the cooling system of an automobile because it absorbs a lot of heat and it doesn't raise its temperature very easily. So it's a good heat absorber. Water is. Okay, so it's a very high specific heat. Okay, so specific heat is a number that tells you something about the ability to hold or grab energy and how fast you get warm as a result of doing that. Okay, metals, low specific heat. It doesn't take much heat to warm them up. Water, high specific heat. Takes a lot of energy to heat up water. Now, you might have noticed something that I put down 4,190 joules per kilogram. That's also 4.19 joules per gram to heat up water, 1 degree Celsius. It takes 4.19 joules to heat up 1 gram of water, 1 degree Celsius. Now that is the specific heat of water. That's also the definition of a calorie. Earlier I was talking about calories, and they're not very big. The chemistry calorie is small. It takes 4.19 joules of energy to increase 1 gram of water by 1 degree Celsius. So that's what a calorie is. That's the definition. Okay, the amount of heat it takes, 4.19 joules, to raise 1 gram of water 1 degree. So it's the amount of heat it takes, actually. Technically, a calorie would be defined as the amount of heat, which is 4.19 joules. So that means that a joule, once again, isn't very much. If you think about it, 1 gram is not very much. It's about 5 drops of water, depending on how big the drop is. 1 degree, not very much. So a little bit of water, 1 degree, it takes 4.19 joules to do that. So it's not a lot of energy. All right, now, we need to know what specific heat is because we're going to use it in our heat calculations. Here is what's called the heat equation. The heat equation is mass of the material, its change in temperature, and the specific heat capacity. So you can do many things with this. Well, let's try thing number 1. The first problem in the second set, in the last set of this problem down here. A 6.22 kilogram piece of copper is heated from 20.5 to 324.3 degrees Celsius. So we have a change in temperature. We have a mass of the copper. It's in kilograms. Now, we'll talk about that in a minute. Do we have to keep it in kilograms? Can we put it in grams? Or what do we have to do? Calculate the heat absorbed by the copper. So we want to know the heat absorbed by the copper. So we want to know Q. So if I want to know Q, I need these other 3 things. Now, typically on a periodic table, the one that I gave you, the one with all that information on it, it'll have specific heat capacity values for each one of the elements. And it gives that chemistry likes to use, okay, the amount of joules per gram for specific heats, joules per gram degree Celsius. So we're going to use joules per gram degree Celsius. That means I need to put this mass in grams. So we'll stick with that. We don't have to. We can put kilograms here, but then I have to use my specific heat capacity in kilograms. You just got to make sure your units are consistent. So if I want to go with grams, which most chemistry problems are going to use grams, then I'm going to put down the amount of grams, 6.22 kilograms. So 6.220 grams of the copper. All right, now, I need the change in temperature of the copper. Now, the changing temperature of the copper is going to be from 324.3 minus 20.5. Let's do that in our heads. So that's going to be 324 minus 20 is 304. 304.3, but minus 0.5, so 303.8. So that'll be a change in temperature of 303.8 degrees Celsius. Now, some of you are probably saying, since I beat it into your heads at this point, oh, Kelvin, gotta have Kelvin. You always say have Kelvin. Here's a case where you don't have to use Kelvin. It's one of those rare times in chemistry where we don't have to have it in Kelvin. We can put the change in Kelvin here. We can. You'll still get the same answer, but we don't have to. So let's not if we don't have to. So in this case, we don't have to put it in Kelvin, so I'm going to leave it in Celsius, and that's fine. It'll work. One case where it works. I need the specific capacity for the metal that we're talking about here, which is copper. Right? Copper, yeah, copper. So we'd have to look that up. And we'd find that it's 3.85 joules per gram degree Celsius for copper. And notice that's joules per gram, so that's why I put this in grams. Actually, you know what? I just made a boo-boo. Boo-boo. I'm not talking about Yogi Bear and boo-boo. Boo-boo, hey, boo-boo. No, it's 0.385. You know. 0.385. I just remembered that because we got to move it 3 places because it's killing. It's 0.385. Okay. But look it up. Don't trust me. Again, don't trust me. Do the math. Let's do it. Okay. And we should get how much heat that the copper absorbed. Now, how do I know to absorb the heat? Because it said it went from 20 degrees to 324 degrees, and that's getting hot. Okay? That's getting like super, super, super hot. It's like Alabama in the summer hot. How do you do that? You gain energy. You absorb heat. So that's how come I know it's a heat absorption. Okay, let's do the calculation on this. 6220 times 0.385 times 303.8. Enter, and we get 727. Oh, it's a big number. 509. Or, whoa, maybe I did it wrong. I mean, that can't be right. That's a huge number, right? I mean, you can't be correct. Let me write that down. 727,509.86. Of course, this is way more specific numbers. You can't, but I'm going to keep a bunch of them. So let's keep some of them anyway. So let's go with 727,510 joules. And it will be joules because the grams and degrees Celsius would cancel, leaving you with joules. And it's a heat unit, so it's got to be in joules for my answer. That many joules. Now you say, this can't be right, it's too big, too big. Remember, the joule is small. A lot of your joule calculations give you big joule numbers because it's a small unit. The other way of writing this, and you'll see this quite often, is 727 kilojoules. 727 kilojoules. All right. Okay, that's the first problem of the last set. Now, we have uno mas chicatos, and this one's a doozy. Get ready. I'm going to go get a beer.